Power transistors are used extensively in control circuits as both switches and power amplifiers. Power transistors are fundamentally the same as the small signal transistors, but are designed to carry more current. This text uses conventional current flow, which means that the current is assumed to flow from the positive battery terminal to the negative. If you are familiar with electron flow, remember that the theory and numbers are the same. Only the indicated direction of the current is opposite from what you are used to. So just to remember, conventional plus to minus. Let's look at bipolar junction transistors, or BJTs. The bipolar junction transistor, BJT, referred to as a transistor, is a three-terminal solid-state device that operates on electric current much like a valve does on water in a pipe. This concept is illustrated in Figure A, which shows that the transistor has three terminals, the base, emitter, and collector, and that it is connected into a simple series circuit with the conventional current entering the collector and leaving through the emitter. Functionally, this is analogous to the system illustrated in Figure B, where the water is being pumped through a partially open valve. The flow of water can be regulated by opening or closing the valve. In the transistor circuit, the flow of current IC can be regulated by adjusting a small control current in the base IB. The more IB, the more IC. In fact, IC could be 100 times or more larger than IB. There are two basic types of transistors, NPN and PNP, both of which are made from 3 layers of semiconductor material. As illustrated, the only functional difference between the two types is the direction of current flow. The arrowheads of the emitter indicates the conventional current direction. The NPN type is more common and it will be the type used in the following discussions. Under the proper operating conditions, the collector current will be a multiple of the base current. In other words, the transistor is a current amplifier. The forward current gain, HFE, which varies according to transistor type, is expressed as HFE equals collector current over base current, where HFE equals the forward current gain, IC is the collector current, and IB the base current. Inside the transistor, the small base current joins with the collector current to become the emitter current, or the emitter current divides to become the base and the collector currents in the PNP. This is expressed as the emitter current is the sum of the collector and base currents, where IE equals the emitter current, IC equals the collector current, and IB the base current. However, because the collector current is usually so much larger than the base current, a useful approximation is to consider the collector current to be equal to the emitter current, that is, IE is equal to IC, and IB is neglectable. The transistor dissipates power anytime there is a current flowing through it and a voltage is across it. This is expressed as PD is equal to the collector current times the voltage between the collector and the emitter. We have established that the transistor will amplify its base current, but how do we know what that base current is? The base emitter junction acts like a forward bias diode, meaning it must first be given a forward bias voltage, about 0.7 volts for silicon transistors or 0.3 volts for germanium, before any appreciable base current flows at all. Once the base has been elevated to the bias voltage, any further increase in base voltage will start the base current flowing. This is shown in graph form. The biasing circuit of a transistor amplifier establishes a background ballpark DC voltage at the base. The signal to be amplified is then superimposed on this base voltage. One common method of creating the bias voltage is with a resistor-type voltage divider circuit, as shown. Notice that resistors R1 and R2 create a base bias voltage of 0.8 volts, ignoring any loading effects. Consulting the input curve, we see that 0.8 volts would cause a base current, IB, of 2 milliamps. The forward current gain of the transistor is given as 100, so rearranging forward gain equation, we can calculate the collector current IC, where IC is equal to HFE times IB, which is 100 times 2 milliamps, or 200 milliamps. Notice that the load is in series with the collector, so that all the 200 milliamps is going through the transistor and the load. We are now ready to discuss the operation of the simple transistor power amplifier shown. The DC bias conditions have already been discussed in the preceding slide. Now consider an input signal voltage of plus or minus 0.1 of a volt, which is superimposed onto the base through a capacitor. In other words, the input is added to the 0.8 volts DC bias voltage to form an AC base voltage that cycles from 0.7 to 0.9 volts as shown. Referring again to the base curve, we see that a base voltage of 0.7 to 0.9 volts translates into a base current of 1 to 3 milliamps, which the transistor multiplies into a collector current of 100 to 300 milliamps, and all of this current goes through the load. Notice that the output voltage VC is out of phase with the current IC. This occurs because the transistor must lower its resistance to increase the current, and the lower resistance creates a lower voltage drop. Class A operation occurs when the bias point is set somewhere in the middle of the operating range, and the actual output current is above and below this value. In other words, the transistor is biased to be half on so that the input signal can turn it more on or less on from that middle point. Class A operation allows for both positive and negative input voltages to be amplified, but has the drawback that power is being dissipated at all times, even when no input signal is present, because IC is always flowing. In Class B operation, the base bias voltage is set just under 0.7 volts for silicon, which is the point where the transistor is just at the brink of turning on. The advantage of this system is that no power is dissipated when there is no input signal, because the transistor is off. The disadvantage is that it can amplify only positive base voltages for the NPN transistors, or negative base voltages for the PNP. The third biasing possibility is Class C operation, where the transistor is operated like a switch, either full on or full off. The base voltage will be either 0 volts, which will turn it off completely, or high enough, say 1 volt, to turn it on so much that the transistor acts like a short circuit or a closed switch contact. The advantage of this system is that it is very power efficient for those applications that can use the on-off type of power. Applications of Class C amplifiers are discussed in Chapter 7. Power transistors are physically bigger than signal transistors and are designed to carry large currents. In control systems, they are used to provide the drive current for motors and other electromechanical devices. When a transistor has a large current and voltage at the same time, the resulting power, VC times IC, must be dissipated in the form of heat. A typical power transistor is designed to operate up to 200 degrees Celsius or 360 degrees Fahrenheit above the ambient temperature. However, its power capacity is derated proportionally for temperatures above 25 degrees Celsius, as denoted by the spec sheet. The power transistor case has a flat metal surface to provide a thermal escape path for the heat. Therefore, to operate it anywhere near the rated power, the transistor must be mounted firmly to the chassis of a metal heatsink, a piece of metal with cooling fins to dissipate the heat into the air. Many times, the case itself is the collector terminal. If the collector must be kept electrically insulated from the mounting chassis, then a special mica insulator is used, together with a thermally conducting white grease. So heat is conducted, but not the electrical voltage. Let's look at an example. A 100-watt transistor fails, apparently from overheating. The transistor was replaced, and measurements showed that the load current, IC, was 2 amps. VCE was 35 volts, and the case temperature rose to 125 degrees C. What is the problem? Look at the solution. First, calculate the power being dissipated by the transistor. So PD equals IC times VCE, or 2 amps times 35 volts, equaling 70 watts. 70 watts is certainly less than the manufacturer's designation of 100 watts. The actual power capacity, however, will be less in this situation because the case is 100 degrees Celsius over the ambient temperature, and the ambient is taken to be 25 degrees C. Consulting a spec sheet, we find that the power must be derated 0.57 watts per degree C above 25 degrees. We now calculate the actual reduced power capacity of 100 watts minus 0.57 times 100 degrees, or 43 watts. Clearly, the problem is that the 70 watts exceeds the derated power capacity of 43 watts. Apparently, the transistor is not heat-sinked well enough. That is, the heat cannot conduct itself away from the transistor fast enough. Now let's take a look at field effect transistors, or FETs. The field effect transistor, FET, is another 3-terminal solid-state amplifying device. FETs perform the same job as BJTs, but because of some advantages, are becoming more common in power applications. These advantages include high input impedance, high switching speeds, and less temperature sensitivity. There are 2 types of FETs, the junction FET, or JFET, and the metal oxide semiconductor FET, or MOSFET. Both types have 3 terminals, the drain D, the source S, and the gate G. Also, FETs are made to be either N-channel or P-channel. The type determines the direction of current through the device. The FETs discussed in this section are all N-channel. The simple JFET circuit is shown. The load current, IDS, passes through the drain to the source. The amount of drain current is controlled by the voltage between the gate and the source, VGS, as contrasted by the BJT, where the collector current is controlled by the base current. The characteristics of the JFET are described in the characteristic curves shown in Figure B. Notice that the load current IDS is on the vertical axis and the voltage across the FET, VDS, is on the horizontal axis. Each curve represents what happens for a different gate voltage. For example, when the gate voltage, VGS, is negative 3 volts, the IDS will be 0 milliamps. The gate voltage is known as VGS off. When the gate voltage is negative 2 volts, IDS will be 5 milliamps. And so on, until the gate voltage is 0 volts, causing IDS to be 15 milliamps. Because the gate voltage is not allowed to go positive in an N-channel JFET, 15 milliamps is the highest load current, IDS, for the particular FET, and is called IDSS, drain source current with the gate shorted. MOSFETs are particularly important in this course because power MOSFETs, which can handle many amperes, are becoming more popular. In Figure A, notice that the FET symbol, the gate is shown as not even touching the rest of the device. This means that the gate is capacitively coupled, causing a very high DC input resistance and allowing for what is called the enhancement mode of operation. In the enhancement mode, all gate voltages are positive. Consider the sample characteristic curves of a power type MOSFET shown in Figure B. When the VGS is 4 volts, the IDS is 0 amps. When VGS is 5 volts, the IDS is 1 amp. And when VGS is 6 volts, the IDS is 2 amp. And so on, up to the maximum current allowed by the device. For both the JFET and the MOSFET, the input is the gate voltage and the output is the drain source current. The gain of the device is called the transconductance, GM, and is expressed in equation. Gain is the change in output currents over the change in input voltage. The units are in Siemens, which are the units of conductance and are the inverse of resistance measured in ohms. The old units were mho, which is the word ohm spelled backwards. An example of MOSFETs. For the power MOSFET, whose characteristic curves are shown, find the gain. Solution: from the gain equation, we see that the gain, GM, is the change in output current due to the corresponding change in input voltage. Thus, we pick two convenient gate voltages, say 5 volts and 6 volts, which represent a change of 1 volt, and divide that into the corresponding change in load current, IDS. In this case, 1 amp. Thus, 1 amp divided by 1 volt is 1 Siemens.